systems, and then we'll be doing this practice problem. Okay, so we looked at 5.16 last time, but I'll just go over the method we did as a refresher. So we have this system of equations and we just want to solve it. So the first thing we do is we choose one of the variables to isolate and we represent it in terms of the other two variables. So it seems like it's easiest to isolate x out of these two equations since you don't have to divide by any coefficient. So let's do that. So if we rearrange this first equation, we get x is equal to 25 minus 3y plus 4z. So then we can substitute this into our other two equations. So if we substitute x is equal to 25 minus 3y plus 4z into the second equation, we get this. And then if we expand this, we get minus 50 plus 6y minus 8z plus 5y plus 7z is equal to minus 66. And so combining like terms gives us 11y minus z is equal to minus 16. So this is what we get when we substitute our value of x into the second equation. And then if we substitute our value of x into the third equation, we can get this expansion. Which, if you expand once again, you get 50 minus 9y plus 12z minus 2y plus 3z is equal to 7. And then once again, combining like terms should give us 43 equals to 11y minus 15z. So note over here that we moved 7 to the left hand side and we moved the variable terms to the right hand side. So we have these two equations. So now it should be pretty easy to solve for y and z. So we have 11y minus z is equal to minus 16. And 11y minus 15z is equal to 43. So now if you subtract the second equation from the first equation, you'll get 14z is equal to minus 59, I believe. Okay, so then you can solve for z. And then from here you can substitute back into either equations to solve for y. Once you solve for y, you can plug both values of y and z into this equation, and you can solve for x. So this is just the general method you'd use when dealing with three variable systems of equations. So now I'll give you guys like 3 minutes to try this problem, and then I'll be going over it. And also remember that when we were doing two variable systems, we had the possibility for no solutions or infinite solutions. And so that possibility can also exist for three or more variable systems. Okay, so let's go over this problem now. So once again, we have a three variable system of equations. And so we'll try to follow the same strategy where we isolate a single variable and then we substitute that value into the other two equations. So clearly, it would be easiest to isolate z since we have a single z lying around here. You can also isolate y, but we'll just do z for the purpose of this exercise. So isolating z gives us z is equal to 3 minus 2x plus 4y. And now what we do is substitute this value of z into the other two equations. So all we did is substitute in z is equal to 3 minus 2x plus 4y into the second and third equation. So then if you simplify these, you get 8x minus 2y plus 12 minus 8x plus 16y is equal to 7. And you also get minus 4x plus y minus 6 plus 4x minus 8y is equal to minus 14. So if you simplify this equation, you get 14y is equal to minus 5. And if you simplify this equation, you get minus 7y is equal to minus 8. So then if you solve for this, you get y is equal to minus 5 over 14 and y is equal to 8 over 7. So when we solve the system, we got two different values of y. So obviously it can't be true that y is equal to minus 5 over 14 and y is equal to 8/7. Because if it were true, we'd get the statement minus 5 over 14 is equal to 8 over 7, which is obviously false. So when we solve the system, we got something that isn't true. And that means that this system of equations has no solutions. So on the opposite side, if we got a statement that's always true, so if we got something like minus 5 over 14 is equal to minus 5 over 14, like when we were trying to solve these systems, then that would mean that the system has infinite solutions. So I'll just use this notation for infinity. So does anyone have any questions on anything we did with 3 variable systems so far? Okay, so if not, we'll be going on to some word problems. So let's look at 5.18 now. So it says, at the word store, each vowel sells for a different price, but all consonants are free. The word triangle sells for $6, squirrel for $9, pentagon for 7, cube for 7, and tetrahedron for 8. What is the dollar cost of the word octahedron? So the key thing here is this sentence, which says each vowel sells for a different price, but all consonants are free. So first thing we do is we write down what the vowels are. So we have A, E, I, O, U. So those are all our possible vowels. And let's say that A costs $, E costs $, I costs $, O costs $, and U costs $. So this might look like a 0, so I'll just change it to P. So we say O costs $P. So we also know that all consonants are free. So all consonants are free. So Now what we'll do is we use the information that was provided to us and we try to make us systems of equations. So we know that triangle sells for $6. So since the consonants are free, we can just ignore them. So the vowels in triangle are I, A, and E. So I plus A plus E costs $6. Then we have square costs $9. So the only vowels in square are U, A, and E. So U plus A plus E is equal to 9. Then we have pentagon costs $7. So the vowels in pentagon are E, A, and O, which is 7. Next, for cube, the only vowels we have are U and E, which cost $7. And then lastly, in tetrahedron, we have E plus A plus E plus O, or 2E plus A plus O is equal to 8. So now we want to find the cost of the word octahedron. So octahedron is O plus A plus E plus O, or 2O plus A plus E. So what is the value of this? So I'll give you guys like 3 minutes to try this problem and then I'll be going over it. Oh, it says 2 times O. Oh yeah, I forgot that I changed it to P over here. So remember that an O just costs P dollars. So it says P plus 2P plus A plus E, where an O costs P dollars. Okay, so I don't really remember the answer, so we'll just go over it now. So the first thing we do is we try to make this as simple as possible. So obviously we have a 5 variable system of equations, so this can look a little bit intimidating. But the thing is, we don't necessarily have to solve for every single variable, if that makes sense. Like what we can do is we can use clever substitution. So the first thing we do is we notice that we have u plus e is equal to 7 over here. And then over here, we have u plus a plus e is equal to 9. So we have u plus e is equal to 7, and u plus e plus a is equal to 9. So this means that a is equal to 2. So we just got that a is equal to 2. So now let's look at these two equations, which is e plus a plus p is equal to 7, and 2e plus a plus p is equal to 8. So e plus a plus p is equal to 7, and 2e plus a plus p is equal to 8. So notice that we can rewrite the second equation as e plus a plus p is equal to 8. So from here, we know that e is equal to 1. So now we know that a is equal to 2 and e is equal to 1. We can just substitute both values into this equation here. And we can get p is equal to 4. So we have a is equal to 2, e is equal to 1, and p is equal to 4. And what we want is 2p plus a plus e. So this would just be 2 times 4 plus 2 plus 1, which would be 11. So yeah, 11 would be the right answer. So this would probably be the easiest way to do it, but sometimes it can be hard to notice these things. So I'll be going over another method with just plain substitution. So once again, what we want is 2p plus a plus e. So we'll solve for that. So the first thing we do is we look at this first equation. I plus a plus e is equal to 6. So now notice that the variable I, it doesn't show up in any of these equations below. So that means that if we isolate either of these variables, it won't help solve the system of equations, if that makes sense. Because if we isolate I, so we'll get I is equal to 6 minus a minus e. But there's nowhere to substitute in that value of I again. So it's basically useless. So essentially we can kind of just ignore this equation here, since the I doesn't show up in any of these equations. So let's just ignore that. So now we have u plus a plus e is equal to 9. So it doesn't matter which one of these we isolate since they all have a coefficient of 1. So let's just say u is equal to 9 minus a minus e. So then, let's look at our second equation. E plus a plus p is equal to 7. So once again, let's isolate p in terms of a and e. So we get p is equal to 7 minus a minus e. And note that when you're isolating these variables, you always want to isolate in terms of the same variables. So try to keep on using the same two variables when you're going through the isolation. So for example, in this equation, e plus a plus p is equal to 7, you could have done a is equal to 7 minus e minus p. But we haven't used that p anywhere else so far, so that wouldn't be the best approach. So that's why we do p is equal to 7 minus a minus e, since we used a and e in the equation above. So then we have u plus e is equal to 7. So it doesn't really matter what you choose to isolate here. Let's just say we have u is equal to 7 minus e. So now what we can do, we can equate these two equations. So we solve for u in two different ways. So we have u is equal to 9 minus a minus e, and u is equal to 7 minus e. So we can say 9 minus a minus e is equal to 7 minus e, and this gives a is equal to 2. So then we have u is equal to 7 minus e, and p is equal to 5 minus e. So let's substitute these values into the last equation. So we have 2e plus a, which is 2, plus 5 minus e is equal to 8. So this just gives e is equal to 1. So if e is equal to 1, then clearly p is equal to 4. And once again, we can just substitute those three values into 2p plus a plus e in order to find our desired value. So this is sort of the more time-consuming way to do it, but it's easier to notice. And you just go in order and you isolate variables in a way such that you try to use variables that you used in your isolation before. Okay, so once again in this method we try to be clever and we see which expressions repeat in the system. So for example, u plus e is contained in the expression u plus a plus e. So we can just substitute in and solve for a, and we continue with that same process. Okay, so now let's move on to this problem. So this is a pretty interesting problem, so I'll give you guys 5 minutes to try it out, and then I'll go over it. Okay, so let's try this out now. So what the problem says, in the magic square shown, the sum of the numbers in each row, column, and diagonal are the same. 5 of these numbers are represented by v, w, x, y, and z. Find y plus z. So key information here is that the sum of the numbers in each row, column, and diagonal are the same. So let's say that this common sum is k. So the sum of the numbers in each row, column, and diagonal is k. So that means that v plus 24 plus w is equal to k, which is this first row. Then the second row would be 18 plus x plus y is equal to k. The third row would be 25 plus 21 plus z is equal to k, which would just be 46 plus z. So that would be our rows. So next for our columns, we have v plus 18 plus 25, which is 43, is equal to k. 24 plus x plus z is equal to k. And w plus y plus 21 is equal to k. So the first thing you should notice are these two equations here. 46 plus z is equal to k, and v plus 43 is equal to k. So let's just isolate the variables z and v here. So we have z is equal to k minus 46, and v is equal to k minus 43. So now, let's substitute in these values to our remaining 4 systems. And also we have the information about the diagonal, but I'm pretty sure we won't need that just yet. So in the first equation, we have v plus 24 plus w is equal to k. So k minus 43, which is v, plus 24 plus, oh wait, let's just write down our equations for the diagonals as well, since we want to put down all the information we have at the same time. So v plus x plus 21 is equal to k, which is this diagonal, and this diagonal is w plus x plus 25 is equal to k. So this is all the information that we have. So now let's substitute in v is equal to k minus 43 into this equation here. So we'd get k minus 43 plus 24 plus w is equal to k. So this would give that w is equal to 43 minus 24, which is just 19. So we found that w is 19. So now, let's see where we can find another w. So w exists here, and w exists here. So let's substitute in w is equal to 19 into this equation here. So we'd get 19 plus y plus 21 is equal to k. So this means y is equal to k minus 40. And similarly, if we substitute in w is equal to 19 into this equation here, we get x is equal to k minus 44, I believe. Okay, so to get x is equal to k minus 44. So now, let's just substitute in everything we know into the equation. 18 plus x plus y is equal to k. So we have 18 plus x, which is k minus 44, plus y, which is k minus 40, is equal to k. So if you solve this, you get k is equal to 44 plus 40 minus 18, and this is 84 minus 18, which is 66. So we have k is equal to 66. But the problem was asking for y plus z. So y plus z would be k minus 40 plus k minus 46. So k minus 40 plus k minus 46, which would be 2k minus 86, which would be 2 times 66 minus 86. And this would have value 46. So y plus z is equal to 46. So what we did here is we used the information that the sum of the numbers in each row, column, and diagonal is the same. And we said that the sum is k. So from here, we wrote down our 8 systems of equations for the rows, columns, and diagonals. And from there, we first picked out our easiest equations that only have 2 variables, and we isolated them in terms of k. And from there, we just substituted in those values, and we solved for the rest of them. So essentially what we did here is just step-by-step substitution, and the process that made this simpler was just realizing which of the variables would be easier to isolate. And in this case, it was z and v first, because those only have the values z and k or v and k, while the other expressions have something like x plus y and k. So yeah. So does anyone have any questions on this problem? Okay, so if not, I think that's it for today. So thank you both for attending, and I won't be assigning new homework, so you guys can just work on the old homework. So thank you.
Thank you.
No problem.
Bye.
Bye.